I'm going to implement one of the simplest algorithms from the reinforcement learning, that is the policy iteration, and we will do this on one of the simplest problems from IL, that is the frozen lake. So we got the imports already. Let's set up the environment. We use the gym to find the frozen lake, that is version 1, and let's make it easy. That is non-slippery, which makes the environment deterministic. We can check the number of states. That should be 16 for the default version. Let's get the action space. There should be 4 actions for going to the left, down, right, and up. Since we're doing policy iteration, this is a dynamic program method that's tabular, so we can access the transition probability functions from the environment, that is P. They should look like a dictionary, where for each state it shows what's going to happen after taking any action. So for instance, when we're in state 0, we can take action 0, 1, 2, or 3, and here we that means that with probability 1 we will transition to state 0 with a reward 0, and we did not terminate the episode, which means that we're gonna stay in the same state, because when you try to go left in the first state of the frozen lake, you stay in the same place. Okay, fantastic. In general, we will want to create a loop that allows us to iterate over our policies and evaluate them, right? So when you take a look at the algorithm, we have the policy evaluation and we have the policy improvement part. So first we're gonna do the policy evaluation, and then we're going to do policy improvement. So here we have to start with some value functions, and that means that for each of the states we're gonna assign value of 0 just for the beginning, and for the policy let's assume an arbitrarily random policy, right? So there are 4 actions that we can take. So that means that for each state we can, this is going to give us random integer integrating a random action that we can take. So for the policy evaluation, we'll have to create some function that's going to be called just policy eval. It will essentially evaluate our policy, our values in the states for the given policy. So we have to pass here value, we have to pass the policy. Okay, and so this has some starting value function and some policy, right? So now we want to simply follow the algorithm, right? So while it's true, we define some delta, that is 0, then for state in range n states. So for each state essentially we're going to create old function that is we have to store the current value at the state because we will be changing it, and the action is just current action that we want to take based on the current policy. And now we can reset our value at the state to 0. So now we have our P that was defined here, and as I said, for something and P state action, so this is going to be a tuple, right, with those 4 things. I'll just print it very fast just to show you what it is. whatever. Yeah, it's fine, it can run. But essentially, you see this is the probability of transition, next state, reward, and whether it's terminated or not. So we can take out our tuple to be probability, next state, reward, and in that case, honestly, we don't really care about the last value. So looking at the algorithm, just following what we have, we multiply probability by the reward plus the gamma that we have not defined yet. Maybe we should do that here. Gamma, let's just be 0.9. It doesn't really matter. Could be 1 in this case. This is a very simple problem, so it should work for all of them. So the delta is the maximum between the current delta and the absolute value between our old value and our updated value at the state, right? Yeah. So this is very trivial, just following the algorithm. And if delta is smaller than our theta, then we will just break, and we can return the updated value array. Let's keep it very small. Let's define it. Great. So we have our policy evaluation. So when we run it, it should we can actually print our. So at the beginning it's just all zeros. After first evaluation, I suspect it to also be all zeros actually. Yeah. So we didn't really change anything, which is fine. But now we have to do the policy improvement. So in that case, we have to know if it's stable, the policy. That means if it changed or if it did not change. And our helper function will allow us to do that. We pass the old policy, and technically, if it will be stable, then we'll want to break. And that's essentially the end, and that's how we found the new policy, so to say. But let's keep it policy. Okay, so we need to add this function, just v policy. Okay, simple. So again, following the algorithm, this is true. The new policy, because it might change now. This should be number of states. Oh, these are all integers. So for state in range and states, it's all the same. However, now we have to check what are the values for each of the actions, so that if we find a better action, this will be the action that we will be taking in the next evaluation of the policy. So what we do is we have to create, let's say, action values, which are just defined into zeros at the beginning for each of the action. Very simple. And then for action in our range of n actions, we will do essentially the same thing that we did here, right? But now we will be just updating the action values for the current action as per the algorithm. Yeah, just making sure everything is correct. Yes, it's correct. And now our new policy is just the argmax of those values for each of the actions. Okay, sweet. So now, if our new policy is not the same as our old policy, that means that our policy is not stable, and we should return that so that we keep on iterating alongside with the new policy that we found. Okay, should work. And now that actually should be all. So we can print the policy. First of all, let's see how many iterations it took us. And we can print the policy that we had at the beginning, and that should be we can reshape it so that it's easier to see what's actually going on. Yeah, and after completion, let's see. You see, so this was random at the beginning, and now it found some policy that's actually working, which is good. It seems like it's working. Obviously, I didn't update this, but yeah, it takes 7 iterations to find the optimal policy. So now, technically, we can see the agent and check how the agent is solving it. We need to change the render mode to human, and we also need to get the state, get the info, and reset. Very simple. Done. Say it's not done. So while not done, let us pick the action. But first, I'll show you what's happening with a random policy, right? So when we pick the action and action space, we sample the action, and then state, we actually don't care about those for now. Just want to show you what's happening. Yeah, when we just keep on taking random actions, okay, yeah, it's just walking, falling over. So now nothing's happening because I didn't reset the environment, right? Okay, technically it's like if it's terminated, if it's truncated, then done equals term or trunk, and let's say done, then we can reset the environment. So yeah, it's just walking. Yeah. So it can't really find the solution. But if we use our policy to pick the action now, we take the action as policy state. And that's essentially it. No need to reset. We can print the reward at the end. It should be 1 because it found the treasure. Okay, let me run it again. You see, it's working. It finds the treasure. Okay, thank you. Super simple.